So today we are going to discuss about, first of all, elastic collision in 2D. Okay, what do I mean is, let's suppose there is a mass which is moving with a velocity something like this, okay, u1, and there is some other mass such that their line of impact is not like this is an oblique collision, right? Because this is center of mass, this is center of mass, and when we are going to join them, the direction of velocity, initial velocity, is not along the direction of line of like the line of motion. This is the line of motion. This is not along the line of impact, right? So this is the oblique collision. So let's say it is moving in this direction at the velocity u2, and after the collision the condition becomes something like this, that let's say this has a mass m1, this has a mass m2, and now initial line of motion was this, and with respect to this is moving in this direction u1, it's moving in this direction u2. The angle which it is making here is theta 1, and angle that this is making here is theta 2. Okay, again m1 m2. Okay, now how to solve these types of questions? So Pranav, do you remember what were the two sufficient and necessary conditions required for anyone to say that the collision is elastic?
Uh, if it's, we could also say it's
Momentum conservation
and
and
if the
like there was one more parameter that was conserved in elastic collisions.
speed or velocity.
No,
No, not velocity. Sorry. It was
we're not revising. Kindly revise the lectures. Okay.
yeah.
So these were the two necessary and sufficient conditions for anyone to say that yes, the collisions that are happening are
Uh,
elastic. Okay?
for kinetic, isn't in kinetic energy conversion, isn't it not like conserved in the middle stage?
Yeah, it is conserved in the middle state as well for elastic collisions. But again, when we are writing the equations, we are not talking about the middle stage. Okay, we are just talking about the initial and final stages because only two equations we need, right? Okay, so when we are going to apply momentum conservation, here we'll have to apply the same thing in what? In two directions. Initially, when we are discussing, the line of motion was equal to the line of impact, right? Here, the line of motion is equal to the line of impact. So, when we applied the collision conditions, we simply applied momentum conservation and kinetic energy conservation. And when we applied momentum conservation, it was only in the horizontal direction. See, right?
Yeah.
But here we'll have to apply the same thing in horizontal direction as well as the vertical direction as well, because this is an oblique collision. This is not a like, or you can even say that even if it is not an even if it is a like direct collision, like where line of motion is equal to line of impact, even if it is that type of collision, still the object are moving something like this. So we'll have to apply momentum conservation in two directions, x and y. Okay, so what will happen, like when we are going to apply momentum conservation in x direction, what will we write? Initial momentum is what? In x direction, m1 u1 plus m2 u2. Is that right?
Yeah.
Pranav, m1 u1, initially x direction velocity is only there for
Yeah.
these two blocks, right?
Yeah.
M1 u1 plus m2 u2 would be the what?
The
This is
equation.
v1, this is v2. This is the initial momentum of the particles combined in the x direction. And the final would be what?
The final would be
We'll have
m
to break these components. V1 cos theta 1, V1 sin theta 1. And here it would be V2 cos theta 2, V2 sin theta 2. Okay, now tell me what would be the final momentum in the x direction?
final one
M1 V1 cos theta 1 plus
m
M2 V2 cos theta 2. Right?
yeah,
This will be our first equation. In y direction, if we are applying, the initial momentum in the y direction is what?
the initial velocity in the y direction was 0.
Yeah, so initial momentum in the y direction for both the particles will be
0.
exactly, because there is only horizontal velocity initially, no vertical velocity. So vertical momentum would be zero for both of the particles combined. And the final would be what?
Um m1 times v sine theta 1
Mm-hmm.
uh minus
Exactly.
because it's downward, so it's
Yeah,
v2
yeah, very good, very good. Full
v
points for that. Okay. So m2 v2 sin theta 2. So these two are the equations, and when we are going to apply kinetic and energy conservation, the initial kinetic energy is what? Half m1 u1 square plus m2 u2 square. Is that right? And the final kinetic energy is what? See, kinetic energy when we are writing, then we only talk about the net velocity, half m1 v1 square, not these two individual velocities. Okay. So kinetic energy will be half m1 v1 square plus m2 v2 square. Okay. This will be our third equation. So when we are going to solve these three equations, we are going to find out what are the necessary values. Some values would be given to you and some values you would have to find out. And in order to find out those values, this will be your go-to method. Okay, apply momentum conservation and apply kinetic energy conservation. But the only difference from the previous condition being that here you will have to apply momentum conservation in both the directions, x as well as y. Okay, any doubts?
no.
Okay, let's do one question now. So here there is a mass m. This is moving with a velocity v naught towards another mass, again m, which was initially at rest. Okay, and after collision what happens? Shaky, shaky. Okay, after collision what happens? That a moves uh, in this direction at an angle theta with a velocity v. Okay, and the second particle moves in this direction at an angle 45 degree. Okay, okay. So the question is find v and theta. Obviously v you have to find in terms of v naught. Okay, you would like to try this question or would you like me to try it?
Um yeah, I would like you to try it so I can solve it
Okay,
a little.
okay, no problem. So what two equations do we have to apply? Simply momentum conservation and kinetic energy conservation. So first let's apply momentum conservation. First I am going to apply in x direction. Okay, it will be initially mv naught plus 0 is going to be equal to mv cos theta plus what is the velocity here? Let's say it is v only. Okay, plus mv cos 45 degree. Now, if I'm going to solve this down, this is going to be V naught is equal to V cos theta plus 1 by root 2. This is my first equation. Now I'm going to apply. See, is this okay for you? Whatever I have written here? Because if I'm going to break these velocities down into components, if I'm going to break these velocities down into components, this is going to be V cos 45 degrees in the x direction, and in the y direction it is going to be V sin 45 degrees. Okay, and here it is going to be V sin theta above, and in the x direction it is going to be what? V cos theta. Okay, that is why I have written initial velocity mv naught plus here it is at rest, so 0 is going to be equal to m into v naught cos theta plus m into v cos 45 degrees. Okay, everything clear?
Yeah.
Okay. Now if I am going to apply momentum conservation in y direction, what is it going to be? Initial y momentum would be what?
Initial y momentum would be 0.
Is equal to mv sin theta minus mv sin 45 degrees. That's right.
Mhm.
Means again m will be cancelled out as well, and v would also be cancelled out, right?
Yeah.
So what we get, sin theta is equal to sin 45 degrees. It means theta is equal to 45 degrees, right?
Yeah.
One of the results we have already got. Okay, okay. And see, uh like this kinetic energy conservation we won't even have to apply because we can directly put the value of theta here. What will be it? We are going to put it here. It will be V naught is equal to V. Cos theta would again be 1 upon root 2 plus 1 upon root 2. So V is going to be equal to what? This will be 2 upon root 2. It means root 2. So V will be V naught upon root 2 answer. Okay. Any doubts? Take
Uh,
a good look at the whole question, and at any part, if you are facing any kind of doubt, please let me know. Okay.
yeah. Okay.
Everything okay?
Mhm.
And here we were fortunate enough that we didn't have to apply the kinetic energy conservation. Okay. Okay. Let's try the next thing.